Hi, everyone. Welcome to Psych 3530, Advanced Research Methods and Statistics. Today, to start off the semester, we're going to do a little review of hypothesis testing. Now, this is not meant to be a... Oh, sorry about that. This is not meant to be a complete and exhaustive explanation of hypothesis testing, but rather to hit some of the high points that you should have been going over in 3510, sort of getting us all up to speed, reminding us of these major points so that we can hit the ground running with some new statistical tests and some new methods for hypothesis testing here in 3530. So, the first thing we need to talk about is the normal probability distribution, often called by a few different names, most commonly the normal curve. Basically, this curve represents the frequency of scores in a population on any normally distributed variable. So we're talking height, we're talking weight, we're talking IQ, how quickly can you run a mile, what's your GPA, how many car accidents have you been in your life, what is your score on a depression inventory, any variable that describes a quality of a human, provided it is normally distributed, can be fit to this distribution. Now, what do we mean by normal distribution? We mean that the majority of the scores indicated by the height of the curve here, right? So where the curve is highest, we have the most people achieving that score. The majority of scores are right at the mean, right at the average. So if the average, and this is the example we're going to use here in just a couple slides, if the average male height is 5'10", then this value on the x-axis right in the center would indicate 5'10", and the height of the curve, so here at its peak, its highest point, indicates the number of men who are 5'10", right? And the most common height for a man is 5'10". The curve is the highest at this point. As we move to the left or below 5'10", right, men are getting shorter and shorter and shorter, and there are fewer and fewer of those men in that curve. And the same thing is true on the positive side of the curve. As we move to the right, height gets more extreme in the sort of tall direction, and we have fewer and fewer men who are that height. Now, this curve is important because what it allows us to do is make statements or decisions about the extremity of a score. And if you remember back to hopefully your previous discussions of hypothesis testing, the process of hypothesis testing is all about deciding, is a score extreme enough to convince us? So scores that are typical, that are in the sort of the meat of the curve, this section of the curve where most people fall, are not convincing, right? If I told you that I have a high IQ and my IQ came back right here as average, then you should not believe me, right? Because I claimed to have a high IQ and my IQ turned out to be very typical. Versus if I claim to have a high IQ and I score way over here in the sort of in the high portion of the IQ curve, right? If this is the average, then moving to the right on the x-axis indicates an increase in IQ. And as IQ increases, there are fewer and fewer people who have that IQ. So if I told you, if I claimed that I have a high IQ, and then we measure my IQ, and I'm right here on the curve in this far extreme tail, then you should believe me because I have shown an extreme score, an unlikely score in the direction of my claim. And so that extremity acts as support for my claim. You're more likely to believe my claim that I have a high IQ if I have an extremely high score than if I have a common or middling score. So this curve can also be broken down into these sort of standard percentages based on standard deviations. You should remember those from 3510. Think of standard deviations here indicated by our 1, 2, 3, 4 to the right and our negative 1, 2, 3, 4 to the left. Our standard deviations are sort of a way that we quantify the spread of a data set, or how spread out versus how condensed to the mean is a data set. When a variable is normally distributed, what that means is that these percentages of the population fall between standard deviation markers every time, all the time. Right? We can say that 50% of people are above the mean, but we can also say that 34.1% of people are between the mean and one standard deviation above the mean. We can say that 13.6, right, roughly give or take, percent of people their score falls between 1 and 2 standard deviations above the mean. And then the curve is symmetrical, so the same is true going below the mean. You have 34.1% of people between the mean and 1 standard deviation below the mean as well. So let's make this a little more real. Let's imagine, like I said earlier, that the variable we're depicting here is male height. We know that the average male height is 5'10", that's 70 inches, and that male height has a standard deviation of 4 inches. So the average goes right here. This high point of the curve indicates the percentage of men who have a height of 5'10". It's a lot of them. It's the most common score. And then as we move out along the x-axis, each of our jumps to a new standard deviation indicates a shift of 4 inches from the mean. So what that means is that if the mean is 70 inches, 5'10", then men who are 1 standard deviation above the mean have a height of 74 inches or 6'2". Men who are 2 standard deviations above the mean, we're going to we added 4 inches here because our standard deviation is 4. And we're going to add another 4 inches such that men who are 2 standard deviations above the mean are 78 inches, or that comes to 6'6". We could keep going. 3 standard deviations is 6'10", or 82 inches. And 4 standard deviations is 7'2", or 86 inches. So what this curve allows us to do is say something like, if a man is 74 inches or 6'2", that is much more common than a man who is 82 inches or 6'10". Right? There are not very many people who are 6'10", but there are quite a few people who are 6'2", 74 inches, and there are even more people who are 5'10" or 70 inches. Now, where do we get these numbers? Where do we get the average and the standard deviation? We get that from large population level data sets, right? So this is data coming from probably the Department of Health or something like that, or maybe the NIH, the National Institute of Health, who have giant data sets from millions and millions and millions of men who go to the doctor and they get their height measured. And so we compile all of that data, and then it tells us that the average is 5'10". We do a standard deviation calculation like you learned in 3510, and it gives us the standard deviation of 4 inches. So these data don't just come from nowhere, right? We don't just make them up. They come from real data sets of real data collected with real people. But then we can apply this standardized curve so that we can make decisions about the height of male and the extremity of those heights. So the big thing to learn here is as height gets more extreme, the number of people who are that height in the population decreases, right? You're more likely to see a man who's 5'10" than you are to see a man who's 7'2". That's pretty self-explanatory. Of course, the same is true in the negative direction, right? We're symmetrical here. So we go down 4 inches in height for each standard deviation on the left side of the curve. such that so if this is 5'10", 4 inches shorter is 5'6", still pretty common. 4 inches shorter is 5'2", right? Very uncommon. 4 inches shorter is 4'10", extremely uncommon. And then of course, 4'6", which is almost non-existent in the population. It's there, but the probability of a man being that height is extremely low. And so the same thing applies on both ends of the curve, right? As height gets more extreme in the negative direction, there are fewer and fewer people of that height. So we can then start to answer questions like, is it more common for a man to be 6 feet tall, which would be about right here, right? Because if 6 feet, if average is 5'10", then 6 feet would be like half of a standard deviation above the mean, right? It's about the halfway point between 0 and 1. So we would have the probability of a man being this tall is something around 32, 33%. But the probability of a man being 6'6", which is 5'10" plus 4 inches, the probability of a man being 6'6" is like right around 5%. Right? So it's much more common for a man to be 6 feet tall than to be 6'6" or to be 5'2". So this curve, because it is a standardized curve, it has a special property that its properties are invariant across variables. So let me say that again, maybe in plain English. The properties that we just discussed about percentages and extremity don't change even if you change the variable you're talking about. What will change is the values because you're talking about a different variable. Standard deviations don't change because they're standardized. And then we can fit these variables to the curve and then have the same nature of this relationship between the curve and the variable. So let's look at two examples. Let's say that you are a primatologist and you're studying variations in the number of individuals in a chimpanzee troop. You collect data all over the world where chimpanzees exist, and you find that the average number of individuals, so 0 standard deviations from the mean, it's the mean, the average number of individuals in a chimpanzee troop is 32, and the standard deviation is 6 individuals, such that a chimpanzee troop of 38 is above average, but still fairly common, right? See where it falls on the curve. But a chimpanzee troop of 50 is very uncommon. That's 3 standard deviations above the mean, right? 32 plus 6 plus 6 plus 6. So a chimpanzee troop of 50, we would then be able to say is a very large chimpanzee troop. Just as we could say that a chimpanzee troop of 14 is a very small chimpanzee troop. Notice how without this curve and without its properties, we have no way of knowing what is a normal, what is a large, or what is a small chimpanzee troop. We have to fit these data that we collect to the curve, and then the curve helps us determine extremity of our scores. Now let's completely change our variable. Let's say the number of fights in a relationship per year. Let's say that we're a social psychologist studying romantic relationships, and we want to understand partner conflict. So we collect a bunch of data with people in relationships. We find that the average number of fights in a year is 7, with a standard deviation of 2. So we can then conclude if you have 7 fights per year, you're average, you're normal. If you have 5 fights per year, you're below average, but this is still a fairly typical score because we take our standard deviation of 2 and subtract going below the mean. But if you have only 1 fight per year, that's abnormally low, right? This is uncommon. There are not many relationships that only have 1 fight per year. Just like having 13 fights per year is uncommon on the high end. This would be a lot of fights. You might want to consider breaking up. So the relationship of the curve is invariant to the variable. It doesn't matter if we're talking about male height or chimpanzee troop size or fights in a relationship. As long as we have the mean and the standard deviation for a variable, we can fit it to this curve, and this curve will help us determine extremity. Okay, so let's take an example again from 3510. Let's review z-scores and how z-scores use this curve to help us make decisions in the nature of hypothesis testing. And remember, hypothesis testing is the way that scientists learn about the world, find truth about the world. Someone has an idea or makes a claim. They have a hypothesis, right? What they believe is going to happen in the world. They then go out and collect some data. And then we need to make a decision about whether those data support the hypothesis. So let's say I make a claim. My name is Dr. Sellers, and I claim that I'm extremely intelligent. You demand proof, and you make me take an IQ test, right? Because you're a good young budding scientist. You're not just going to believe what I say just because I said it. You want proof. You want to do an experiment. So you collect data. You make me go take an IQ test, and I score a 122. That's not bad, considering that the mean is 100. And we know that IQ has a standard deviation of 15. Again, we get these data because they're given to us from data that have already been collected, large population level data sets. So this begs the question then, I'm above the mean, 122 is higher than 100. Should we consider me to be extremely intelligent? Is this good evidence to support my claim or not? So in hypothesis testing, we need a standard. We need like a hurdle. We need a line in the sand that if we cross over that line in the sand, it's going to tell us whether the data support our claim or hypothesis. And so we agree, we come to a mutual agreement that in order to be extremely intelligent, I must be in the top 5% of intelligence. This is what we call alpha. So we're going to set alpha at 0.05, meaning that I must be at least in the top 5% of intelligence to be considered extremely intelligent. We find alphas in the social sciences and behavioral sciences, like psychology, to be either 0.05 or 0.01. Those are sort of our common benchmarks in the field. So if I'm more intelligent than 95% of people, right? If I'm in the top 5% of intelligence, then we will consider me to be extremely intelligent. We can express this research question with hypotheses. HO, or the null, the nothing happens hypothesis, is that Dr. Sellers is not extremely intelligent. The null hypothesis is the place where we start. We start with the idea that we do not believe the claim. Science requires support in order for us to believe a claim. So when someone makes a claim, we withhold our acceptance of that claim until they provide evidence that supports their claim. So I have claimed that I'm extremely intelligent. So the place where we start is that I'm not extremely intelligent. The alternative, the H1, you'll often hear this called the research hypothesis, is that I am extremely intelligent, right? It's the opposite of the null. So one of these will be supported, right? I'm either going to stick with my null, or I'm going to shift to supporting the research hypothesis. Here's our formula for a z-score. X, which is my score, 122, minus the mean of 100. So how far away from the mean am I? Divided by standard deviation, or our expected amount of variability in the data. So how far from the mean am I as a ratio of expected distance from the mean in the population? Let's do the math. The math is simple, right? 122 minus 100 divided by 15, plug and chug, gives me a z-score of 1.47. So what this 1.47 means is that my IQ of 122 is 1.47 standard deviations above the mean of IQ. So if we fit me to that curve, I'm right here. We go 1 standard deviation above the mean, and then basically 1.5, 1.47, right? 1.47 standard deviations above the mean. So I'm here. I'm fairly far out on the curve. It looks like I'm more intelligent than a lot of people, right? Everyone to the left of me, look at all the people, right? All the area under this curve. All of these people over here represented by this area of the curve are less intelligent than I am. Anyone to the right of me, represented by this much smaller area of the curve, are people who are more intelligent than I am or scored higher on the IQ test. So the question is, am I in the top 5%? We can put that in we can express that in two different ways. Is this small portion of the curve less than 5%, right? Because if I'm in the top 5%, then there will be fewer than 5% of people above me. Alternatively, sort of the flip side of the same coin, is this large area of the curve greater than 95%, right? Am I more intelligent than at least 95% of the population, right? That would also put me in the top 5. So we need a way of figuring out, where does this top 5% exist? What we can do is use our standard normal probability chart, or what might be called a z-table, since this is a z-score. We take and we find my z-score, 1.47. So here on the left, we look for the first 2 digits, the 1.4. We find the 1.4 here. Never mind that it's negative, right? It doesn't matter that this chart lists them as negative, because the curve is symmetrical, right? The probabilities on the left side of the curve are identical to the probabilities on the right side of the curve, as we discussed earlier. So whether this table says positive or negative doesn't matter. We just have to keep in mind whether our value is actually positive or negative, right? But we just find the digits that we have. So our first 2 digits are 1.4. Our third digit, we come across the top, is 7. 1.47 means that the table returns a value of 7.08%, right? Move the decimal twice to the right to get your percentage. The table returns the value of 7.08. The value that the table returns is the percentage of people in the small area of your curve. Now, this is where we need to be careful. The table does not return the left or the right side of the curve. Remember, we're symmetrical. The table can't tell you whether you're left or right. You tell you whether you're left or right based upon whether your z-score is positive or negative. The value that the table returns tells you the percentage of the population in the small proportion of your curve. So let's go back to our curve. I'm 1.47 standard deviations above the mean. The small portion of my curve is to the right. It's this part. So this value of 7.08 refers to the percentage of people who are smarter than me, who are more intelligent, right? Because that's my small area of the curve, is the area above me. So this means that 7.08% of the population scores higher on an IQ test than I do, which means I am not in the top 5%, right? I'm not. I'm in like the 93rd percentile. I'm close. I'm almost there. But if 7% of people are smarter than me, then I'm not in the top 5%. The point at which I become the top 5%, right, this point of alpha, 0.05, is somewhere to the right of me. I did not cross over my line in the sand. We can think about our calculated z-score being compared to this benchmark of alpha. And if I cross over the benchmark, if I clear the hurdle, if I move past the line in the sand, then we support my claim. But because I didn't cross over the line in the sand, because I'm not more extreme than alpha, then what we're going to do is stick with the null hypothesis. We are going to fail to reject the null hypothesis, right? And think about, it's a double negative, but this is the language we need to use in science. We fail to reject. So remember, we start with the null. We're hugging the null tightly. It's what we stay with. And if I fail to reject the null, it means I keep the null, right? I continue to possess and to hug the null hypothesis. And our null hypothesis is the idea that we do not believe my claim. It's the idea that I am not extremely intelligent. So this z-score of intelligence does not support the claim. It supports the null. It supports the idea that I'm not extremely intelligent because I did not achieve the level of extremity, at least 5% extremity, that we agreed upon at the beginning of the experiment. So what we would do is we could write this up in an APA-style conclusion. Say a z-test was conducted to see if Dr. Sellers is extremely intelligent. We fail to reject the null, z equals 1.47. Our result was not significant. We were not statistically significant. And we conclude that Dr. Sellers is not extremely intelligent. So even though I'm well above the mean, right, even though I'm smarter than basically 93% of people, right, because if 7% of people are above me, then 93% of people are below me, I did not meet the threshold of 5% that we agreed upon. So we conclude that I'm not extremely intelligent. This begs the question, of course, what score would I need to get to that benchmark, right? What score gets me to the 5%? Turns out it's 1.65. How did we find this? It's a little complicated, but basically, you look for the place on the curve where your probability, your percentage, just barely crosses over into the top 5%. And that happens at 1.65 standard deviations. So look, at 1.64 standard deviations, we're not in the top 5% yet because 5.05% of people are smarter than me. It's literally by a hair's breadth, right? I'm almost there, but I'm not in the top 5% because more than 5% of people are beyond me, right? We would be over here on the right side of this curve. But as soon as I score a 1.65, as soon as I'm just that little bit more extreme, suddenly I'm in the top 5% because less than 5% of people are above me. And if less than 5% of people are above me, then I am extremely intelligent. So our benchmark, our line in the sand, if alpha is 0.05, our benchmark for a z-test is always 1.65. Or if I have a hypothesis in the negative direction, it's negative 1.65. So if my result is inside of that benchmark, right, this direction towards the larger portion of the curve, if we're inside of the benchmark, then we're not significant and we fail to reject the null. If we're beyond the benchmark, then our result is significant and we reject the null hypothesis. Okay, let's do an example with a single sample t-test, which you should have gone over again in 3510. This single sample t-test is used when we collect data from a group of people and we find their average. That's what this X bar represents. We compare it to a known population average. This is mu. And we divide by the known standard deviation. That's S. Oh, I'm sorry. Yes, the known standard deviation in our population, S, divided by the square root of the number of people we collected data from. Basically, what we're asking is, does our sample, our X bar, our sample, in this case of 8 people, differ from the known population average of 24? Our research question here is, we want to know if people in cognitive behavioral therapy score lower on the Beck Depression Inventory than average. So, does CBT, cognitive behavioral therapy, lower people's depression? We collect data from N equals 8 people. They scored an average of 15.75 on the BDI, the Beck Depression Inventory. We know that the population scores an average of 24. And here we have our variability in our population, our S. We plug and chug these data into the single sample t-test formula on the left, and we get a t-score. We don't have a z-score anymore. We have a t-score of a negative 3.45. So our participants in our study are below the mean, right? 15.75 is less than 24. The question we need to answer now is, are they enough below the mean for us to claim that cognitive behavioral therapy decreases depression? So we have our calculated t-score. That's analogous to our z-score that we just had. But now we need our line in the sand, what we call our critical t-value, our point of comparison. For t-tests, our point of comparison changes based upon 3 pieces of information: degrees of freedom, which is number of participants minus 1, alpha, and whether we have a one-tailed or a two-tailed test. We'll go over what that means shortly. So we had 8 individuals, which means our degrees of freedom is 7. We're just going to stick with an alpha of 0.05 to keep it simple. And then we had a one-tailed test. Now let's go back to our research question. We want to know if people who are in cognitive behavioral therapy score lower, that's our keyword here, lower on the Beck Depression Inventory. So if we think about the normal curve, we are only looking in one direction, right? We are anticipating that our sample of people will be to the left of the mean because we're anticipating cognitive behavioral therapy will lower their scores. So we have a one-tailed test. We're only looking in one direction. So if you have words like lower or less than or more or greater than, then you have a one-tailed test. Language for a two-tailed test is something like people in cognitive behavioral therapy will score differently or will be not equal to the average BDI. Notice how score differently or be not equal to doesn't have directionality. And so we call those two-tailed tests. We'll get into, we'll review the implications of a one-tailed versus two-tailed test conceptually towards the end of this lecture. But for now, let's use these 3 pieces of information to find our critical t value. So our degrees of freedom is 7, which means I know that my critical t value will be on this row because we looked for at degrees of freedom 1, 2, 3, 4, 5, 6, 7, and we found it right there. So my critical t value, my hurdle, my line in the sand that I must cross, that I must be more extreme than, is going to be on this row. We then need to apply our other 2 pieces of information. I have a one-tailed test, so I'm going to use this row that starts with 0.50. I'm going to use this row and then apply my alpha, which is 0.05, and I'm going to find my 0.05 alpha on that top row of one-tailed tests, which then tells me that I need to use this column. So 3 pieces of information. Degrees of freedom tells me which row to use. Whether I have a one-tailed or a two-tailed test combined with my alpha tells me which column to use. Now, if I had a two-tailed test with alpha of 0.05, I'd be using this next column because we can see 0.05 falls in the next column under a two-tailed test. We'll talk about why that's the case later. But for now, let's just focus on finding these values and using them for hypothesis testing. So degrees of freedom 7, use this column. One-tailed, 0.05 alpha, we use this column, which means my critical value is 1.895. I need to be more extreme than 1.895 in order to be statistically significant. So let's look at the curve. My observed or calculated t-value from my participants in my study was negative 3.45. That's 1, 2, 3, and almost a half standard deviations below the mean because I'm negative, right? Remember, our average was something like 15.75 for our participants. The population average was like 24. So I'm substantially below the mean here. We just found our critical value of 1.895, but because we made a one-tailed negative hypothesis, we're going to put a negative sign in front of that because this table, just like our Z table, is symmetrical, whether you're above or below the mean. So we stick a negative sign in front of it because we made a one-tailed negative hypothesis. So here's our hurdle, our line in the sand, our critical value. That's 1 and then almost 2 standard deviations below the mean. So our calculated value is well beyond the mean. We are more extreme than the cutoff. Therefore, we reject the null and conclude that our participants are in fact lower on the BDI than the average population. It looks like cognitive behavioral therapy significantly reduces depressive symptoms. And we can say that because we crossed over this threshold. Remember, extremity is convincing. We are convinced by extreme results in the direction of our claim. We claimed that therapy is going to reduce depressive symptoms. And we see that that's exactly what happened. This is the average depressive symptoms in the population. People who are in therapy are way over here below the mean. Therapy reduced depression so much that we crossed over our threshold, our critical value, and thus we can claim that therapy works. We also maybe want to look at an effect size. We'll go into this more. It's not super important here for hypothesis testing. We'll get into this more throughout the semester. But an effect size is a way of calculating the magnitude of our effect. I've got a little formula for it here. Don't worry too much about it. But our effect size is going to tell us, is our effect small, medium, or large? We have a large effect size here. And so what it means is that we have a statistically significant and a robust effect, meaning that it is both statistically significant and probably very important. We could write this up in an APA-style conclusion like this, where first we introduce the test and research question. A single sample t-test was conducted to see if psychology majors score lower on the BDI than the average college student. Next, we state whether we reject or fail to reject the null. Remember, we reject the null because they are more extreme. The null would be that they are not extreme, but they are, so we reject the null. A significant difference was found between psychology majors who had a mean of 15.75 and a standard deviation of 6.76, and the average college student whose mean was 24. This is where we identify our groups and we state our descriptive statistics. Next, we have our statistical statement, or maybe you could call it our T statement. T, parentheses, degrees of freedom, so 7, is equal to our calculated t-value of -3.45, comma, our effect size, d equals 1.22, We put the absolute value of our effect size here. Doesn't matter that doesn't need to be negative because the effect size quantifies the size of the effect, not the directionality of the effect. And then P was less than 0.05. Remember, our alpha was 0.05. P is less than 0.05. What this is telling us is that the probability, the P, of our results of getting a T of negative 3.45, the probability of that happening was less than 0.05. Let's think about what that means here, right? Our critical value is the place on the curve that chops up the curve into 95% in the big direction and 5% in the small direction. So what we're saying is that the probability of this, our calculated T, our observed effect, the probability of this observation is less than 5%. So that's what we say with P is less than 0.05. And then we provide a take-home message, a conclusion. We want to make this very simple to understand. I always say, explain it to a 10-year-old. So thus, psychology majors. Oh, I think that's the wrong example. My bad there. Our question was not about psychology majors. Sorry about that. Used the wrong paragraph here. Our question was about just people in cognitive behavioral therapy. Thus, scratch this. People in cognitive behavioral therapy have lower depressive scores than the average person. My bad for that mistake. I'll go back and fix that on the static PowerPoints. Okay, so now let's talk about whether we have a one-tailed or a two-tailed test. So a one-tailed test makes a specific prediction. It will have with directionality. So it'll have words like less than, more than, faster than, slower than, bigger than, smaller than, words that indicate directionality of a prediction. And so what we're doing in a one-tailed test is we're setting up our hypothesis to be in only one direction. Right? So we find our critical value wherever it is, and we're asking, do our data fall beyond the critical value only on this side of the curve? However, you can make a two-tailed hypothesis. A two-tailed hypothesis is non-specific, meaning we don't have directionality. This will have language like different from or deviate from or change, things that don't say greater than or less than, just different. Now, reasons why you might want to make a two-tailed hypothesis are that you're unsure of what the results are going to be. You're maybe doing an exploratory experiment that's never been done before. And so you're not sure whether your manipulation is going to maybe increase scores or decrease scores. So you want to sort of give yourself the opportunity for a significant finding on either side of the curve. Let's say that our alpha is 0.05. If our alpha is 0.05, then we have to split that 5% and give half of it, 2.5% of it, to the right side of the curve, and half of it, 2.5% of it, to the left side of the curve. Or if our alpha was 0.01, we would split the 1% and give 0.5% on the right side of the curve and 0.5% on the left side of the curve. What this is going to do is make it more difficult for us to achieve statistical significance because now there's less room over here, right? We need an even more extreme finding because instead of all of our 5% being on one side, we're splitting it from 2.5 to 2.5. So let's maybe look at this with an example. Let's say we have an alpha of 0.05 with degrees of freedom of 10, and I have a positive one-tailed hypothesis. Athletes will bench press more than the average student. Here's my critical value. I have my 5% because my alpha is 0.05 is in this direction, right? Only because I'm saying athletes will bench press more. So this is how I would set up my line in the sand. I would then go collect data with athletes and see if they fall in this small area of the curve, in which case I conclude that they do bench press more. But let's say for some reason I'm unsure of whether athletes will be able to bench press more or less, I'm just going to make a two-tailed claim or two-tailed hypothesis. Athletes will bench press a different amount of weight than the average student, meaning they could bench press less than the average student, or they could bench press more than the average student. So, because I'm saying a different amount, I'm giving myself the opportunity for athletes to be significantly lower or for athletes to be significantly higher than the average student. Still have the same alpha of 0.05 with degrees of freedom 10. What would end up happening here is I take this 5% of extremity that I'm going after, and I put half of it on the left for 2.5. I put half of it on the right, another 2.5. And so what this does is it pushes my critical values out further. Notice how they are positive and negative 2.228. That's more extreme than my one-tailed hypothesis, which was 1.812. So a one-tailed hypothesis makes it easier to achieve statistical significance, but I only get one direction in order to be correct, to be right. A two-tailed hypothesis makes it slightly more difficult to achieve statistical significance. We've bumped out our lines in the sand, our critical values a little further, 2.228 and negative 2.228. But I get a chance on both sides. I get to be right in the negative way, or I get to be right in the positive way. Okay, so let's work on identifying these hypotheses. We have three types of hypotheses. We have one-tailed positive, one-tailed negative, or two-tailed. So I want you to maybe press pause and take a minute or two, go through each of these 5 examples and try and determine whether they are a one-tailed positive, a one-tailed negative, or a two-tailed hypothesis. Go ahead and press pause and then press play when you're ready to go through the answers. Okay, hope you're back. Hope you looked at these. And let's determine our answers. Do 8-year-olds cry more than 10-year-olds? That's one-tailed positive. Do they cry more, right? That's a positive directional hypothesis. Do people from New York City differ in the number of curse words they use than people from Atlanta? That's two-tailed. I'm making no assumptions about whether people from New York might curse more or less than people from Atlanta. I could find that they curse less. I could find that they curse more. I'm just wondering if they differ, right? There's no directionality there. So that's a two-tailed hypothesis. Does a medication increase side effects? Right? Increase is our keyword here, so it's one-tailed positive. Does mindfulness meditation reduce scores on a measure of anxiety? That's one-tailed negative. And do Boston Terriers have a different lifespan from German Shepherds? That's two-tailed. All right, that's it for this review of hypothesis testing. Again, sorry for the little mistake with the wrong paragraph there from our example. I must have changed that at some point and forgot to go back in and copy paste the new example. But I'll go back and make sure that's done on the static PowerPoints that'll be on iCollege for you so you don't get confused. If you have any questions, reach out to your instructor because we will really be building on these ideas pretty much right away in the class. You need to have a good grasp conceptually of this hypothesis testing model as we move forward and start to add more and more statistical tests to this framework. So thanks everybody, and I will talk to you later.